Today we're going to talk about relative extrema of multivariable functions. All right, what the heck does that mean? So when you have a relative extrema, we're talking local min, local max. Well, in 3D, we have local min, local max, and we have things called saddle points, which is kind of like the middle of a Pringle. So that is what we are going to discuss today. So relative extrema, just like they were in two-dimensional calculus, is based on the definition of a critical point. In two-dimensional calculus, a critical point is when your derivative equaled zero or didn't exist. Except now, I have more than one derivative, so I just need them both to equal zero or either one of them to not exist. So if f is defined on an open region R containing x sub 0 and y sub 0, your point is a critical point if both f sub x and f sub y equals 0, or if either f sub x or f sub y do not exist. Then you have a critical point, and that tells you, hey, something funky's going on here. Could be nothing, could be a saddle, could be a max, could be a min, or it could just be like a pointy, cuspy, weird thing. Okay? Now, last year, when we wanted to test whether something was a max or a min, we had the first derivative test, where if your first derivative went from positive to negative, then your function went from increasing to decreasing and you had a max. There was also the second derivative test that said if you have a max, that means at that point you're also concave down, which means that at your critical point, you could do the second derivative test, plug that critical value into the second derivative, and see if your second derivative is positive or negative, deciding if it's concave up or down, telling you if it's a max or a min. Except now I don't have a second derivative. I have three. I have f sub x, f sub xx, f sub yy, and f sub xy. And basically, we need to find a way to smash them all together to figure out the concavity of a surface instead of just a curve. All right. So in order to do that, we define a new value called d, where d is f sub xx times f sub yy minus f sub xy squared, evaluated at the critical point. Okay. Why, you may ask, do you do it this way? The answer lies in a Taylor series approximation to a multivariable function. And before you break into a cold sweat, I am not going to go into the proof right now on the video, though the proof does exist, and maybe I'll make another video, or maybe I'll find somebody else who already did and assign that later. All right, so if I have a critical point, and that critical point is one where the first derivatives both equaled 0, I plug that critical point AB into this D equation, and then I see what happens. If D is greater than 0 and f sub xx is greater than 0 also, we consider that we have like a concave up multivariable surface giving us a min. If D is greater than 0, but f sub xx was less than 0, then we consider that it's concave down and we have a max. If D is negative, if D is less than 0, then we automatically have a saddle point. Again, think Pringle. And the test is inconclusive if D equals 0. So if D equals 0 at your critical point, what you do is test other points around that and see if you get higher or lower Z values, and then decide from there. Let's go. Find and classify the relative extrema and or saddle points for z equals negative x squared minus y squared plus 4x plus 8y minus 11. Well, right off the bat, I can tell you that this is a paraboloid that's opening down, so I know I'm going to have a relative max, because if we graph this, it's going to look like an upside down paraboloid. Okay, so I'm anticipating a relative max, but let's see how we can prove that numerically. All right, so there's z. So f sub x is going to be what? Negative 2x plus 4. I want to know when that equals 0, and that's going to be when x equals 2. F sub y is negative 2y plus 8. I want to know when that equals 0, and that's going to be when y equals 4. So the only critical point I have is the 0.24. Now, I'm curious, is this going to be a relative max or a relative min? To know, I've got to look at my second derivatives. So I'm going to find f sub xx, which is just -2, f sub yy, which is also -2, and f sub xy, which in this case is going to be 0. All right, so I'm going to find d, which is f sub xx times f sub yy minus f sub xy squared, and that's 4. Since d is greater than 0 and f sub xx is less than 0, we know that our critical point is going to be a maximum. Okay, that's what we had up here in number 2. So I know the point 2, 4, whatever the z value is a relative max. And let's go to GeoGebra just to make sure. Bloop. And what do we have here? Negative x squared minus y squared plus 4x plus 8y minus 11. So f sub of xy, negative x squared minus y squared plus 4x plus 8y. I want to say it was plus 11, minus 11. Oh, so close. All right, so here's my graph. I can't see all of it, and, my big face is in the way. So let me zoom out a little bit. Oh, look at that. Look at that happy little parabola. The paraboloid, I should say. Yeah, I definitely have a relative max. Let's see, where is the 0.24? It's going to be at 249. So this point right up top here is the 0.249. And I'm pretty confident that that's a max. Cool, cool. All right, let's do it again. You know what? Let's look at it first before I close my computer. X cubed plus y squared. All right. F of xy, x cubed plus y squared minus 3x squared plus 10y plus 6 plus 10y plus 6. All right, that doesn't look like a whole lot. Let me zoom out a bit here. Oh, I'm starting to notice some things here. One more. Oh, okay. Now I can see it. I wish there was an easier way to kind of zoom on this, but there's not. So if we look at this, how would I describe this? You know how I describe this? I would describe this thing as kind of like I don't know, it's got like a nose of a missile or something laying on a table. I'm trying to turn this in a way that you can see it, but it's just, there we go. So it looks like what I have is, if you can see it right here, I've got a relative min, and then right there, I have a saddle point. And if you're curious what the heck is a saddle point, if you look from this direction, that point right there is a relative max. But if I turn it very carefully, ooh, you can even see it right here, coming from the top, that's a relative min. And the reason we call it a saddle point is because it looks like a saddle. When you sit on a saddle, you got like the front part coming up in front of you, the back part going out behind you, but your legs can go down the side. All right, so I anticipate here I have a relative min and I have a saddle. Let's see if we are correct, which is not guaranteed. Let's be honest. I'm recording this in 2021, so just in case I use this at a later time, just so you know, everything sucks here. We're basically living in, I don't even know, some chaotic wasteland, and nothing ever works the way I want it to this year. And if you're currently watching this in 2021, like many of you are, just know I'm doing my best. All right, let's see. Do I have a relative min and a saddle point? I'm not sure. I don't know where they are. Let's find out. So here is my equation. F sub x is 3x squared minus 6x. f sub y is 2y plus 10. And I'm going to set these both equal to 0. And if I factor out a 3x here, I get x equals 0 and 2. And this would be y equals -5. So our critical points are going to be the point 0, -5, and 2, -5. All right, I need to throw those in D. So I have to find f sub xx, which is 6x minus 6, f sub y, which is 2, and f sub xy, which just so happens to be 0 again. That doesn't happen all the time. It just happened twice in a row. It's fine. All right, now I want to find D for the point 0, -5. So f sub xx is going to be, well, let's see, at x equals 0, f sub xx is -6, f sub y is 2, and f sub xy squared, that's going to be -12. Since D is less than 0, that makes a saddle point at the point 0, -5, whatever z is. And if I find the D value for 2, -5, when x equals 2, f sub xx is going to be what? 12 minus 6, which is 6. F sub y is still 2. F sub xy is still 0. I get positive 12. D is greater than 0. F sub xx is greater than 0. That means we have a min at the point 2, -5, whatever. And that's what I thought I had. So that's feeling pretty good. And let's just go back and figure out what that is. So 0, -5, and 2, -5 is what I need to evaluate here. So f of 0, -5 is -19. And if I change that to 2, -5, nope, that's absolutely not what I wanted. Let's try this again. See what I mean? I'm doing my best, everybody. I don't know what to tell you. F of 2, -5, there we go, is -23. So what I say, -19 and -23? I think that's what I said. -19 and -23. And yeah, when we looked at it, the saddle was a little bit higher than the min. So I'm feeling pretty good. All right. Uno más. Well, there's probably dos más, but one more right now. Find and classify the relative extreme values for this other thing. And again, you might as well look at it. All right, so let's look at it. I have, whoa, what did I just do? I moved things and now I can't see my mouse anymore. Guys, this year, it's killing me. Just killing me. There we go. All right, x plus y, xy plus 1. Come on. You can do it. What I say I got here. X plus y, xy plus 1. Ooh, this is fun. Look at this thing. All right, well, I'm looking at this and I see 2, maybe even 3 locations. And if I zoom out, it doesn't look like any of these turn into a paraboloid. Yeah, I see 2, maybe 3 locations here. And the reason I say I see 3 is because I think about where I could sit here and kind of put my legs. So it looks like I could sit right here and put one leg to the left and one leg to the right. So I feel like I have a saddle point right there. And then I'm thinking I could also sit like over here, right there, and put my leg over left and right. And the same thing over there. I think I have 3 saddle points. So let's find out. All right. What's going to happen now? Bloop. Okay. I know I need to take the derivative. I'd prefer not to do the product rule, so I'm going to distribute right now and make this x squared y plus xy squared plus y, because I think that's going to make it easier to take my derivatives. So I know that f sub x is going to be what? 2xy plus 1 plus y squared. Whoa. And I got to set that equal to 0. And f sub y is going to be x squared plus 2xy plus 1. And I'm supposed to set that equal to 0. Ooh, they both have x's and y's. I have a system. I'm going to go for substitution. So if I look at this first equation, I'm pretty sure I can get it into x equals form. So I'd have 2xy equals negative y squared minus 1. And then I'm going to divide by 2y. Negative y squared minus 1 over 2y. Then I'm going to substitute it in over here. So I have x squared, which is going to be negative y squared minus 1 over 2y squared plus 2 times x times y plus 1 equals 0. Okay. Fine. So let's see what happens now. These will cancel. And when I square this, I really get y to the fourth minus 2y squared plus 1. Nope, that'll be plus 2y squared. Excuse me. Over 4y squared plus, oh, you know what? These 2's cancel. Negative y squared minus 1 plus 1 equals 0. I'm going to cancel that. I don't like the fact that I have a fraction, so I'm going to multiply both sides by 4y squared. And if I do that, I'm really going to end up with y to the fourth plus 2y squared plus 1 minus 4y to the fourth equals 0, which is 3y to the fourth minus 2y squared minus 1 equals 0, because I didn't want a lead coefficient that was negative, so technically I had negative 3y to the fourth and then plus plus, but I changed all the signs to make my life easier. That looks factorable, so 3y plus 1, pardon me, 3y squared plus 1, y squared minus 1. That's not going to equal 0 unless we dip into imaginaries, which, no thank you. Y squared minus 1 equals 0 when y equals plus or minus 1. Whew! All right, so if y equals plus or minus 1, at y equals positive 1, I'm going to have negative 1 minus 1 over 2. So x will equal negative 1. And if y equals negative 1, x is going to equal negative 1 minus 1 over negative 2. And x will equal 1. So I got critical points of negative 1, 1, and 1, negative 1. All right, so I have critical points at negative 1, 1, and 1, negative 1, and now I need to go back and I have to evaluate that D thing. So maybe I shouldn't have written so big, huh? All right, I'm going to use blue just to make it a little bit clearer here. So there's f sub x and there's f sub y. So if I want to find D, I need f sub xx, which is going to be 2y, and f sub yy, which is going to be 2x. And then I need f sub xy, which is going to be 2x plus 2y. That's the first time our f sub xy has been anything other than 0. See, I told you it could happen. All right, so we need to evaluate D for negative 1, 1 and 1, negative 1. So let's see. D for negative 1, 1 is going to be, well, let's see. Negative 2. No, positive 2. Mrs. Bibber, pay attention. So if I plug in negative 1, 1 into 2y, I get 2. If I plug negative 1, 1 into 2x, I get negative 2. And if I plug negative 1, 1 into f of xy, I get negative 2 plus 2. That's still 0 this time. Again, that just so happens to happen for these. It does not always happen. And I have d is negative 4. So I know negative 1, 1 is a saddle point. And then if I do d of 1, negative 1, it's really going to end up being the same thing, but now it's negative 2 times positive 2 minus 0. So 1, negative 1 is also a saddle. Now, if you remember, I thought we would have 3 saddles. We don't. And now I want to go back and explain why. So if I look at this, get my face out of the way. If I look at this thing right here, I definitely have a saddle right here, if you can see my pen moving. Because if I look at that from this direction, the graph goes down and comes back up. It's a min. But if I look at it from this direction, it goes up and comes back down. It's a min from one direction and a max from another. That's what a saddle is. And the same thing happens over here at the other critical value. Now, I thought maybe like right here at the origin, I would have a saddle. Here's why I don't. If I look at that from the front, it goes up and comes back down. But if I look at it from the side, it's really hard to see it, but it goes up and then keeps going up. Now, fun fact, this thing as a whole is called a monkey saddle. I swear to God, that's what it's called. It's so fun. I wish I could get Brown in here. I can't. So we're going to make him an orange monkey. This thing is called a monkey saddle because what does a monkey have that you don't have? There's his little monkey arms. There's his little monkey feet. And what does a monkey have that you don't have? It's got a tail. And his tail will go down this way. So it's called a monkey saddle because there's actually 3 places for appendages to go. And a monkey's got a third appendage on its butt that you don't have. All right. So, I mean, where should I finish talking? I should probably finish talking right now where I've drawn a monkey and let it go. So I hope everybody's having a good day. And we will all talk again later. Have a good one.